Welcome to another exciting image processing class. I've had a terrible problem with my knee after a sailing accident, and I tore one of the important pieces inside, and I needed to go for an MRI. So I went to the advanced radiology imaging place in Fairfield, and I said, "Oh, make me a CD with all my images." And they said, "Okay, they're your images." And so they gave them to me. And now I have them on Dropbox for everybody to see. Unfortunately, they're in some wacky format. And the first thing I like to do is try and figure out what kind of format images these are. So these are real medical images in some real wacky medical imaging format, and I don't know what it is. I think it's called a Dicomed imaging format. So, first question is, how do we determine what the format is of an image? Right? They have no suffix. I mean, you could just say, "Oh, let's take this image here and give it." Yeah, let's give it JPG. Now it's a JPEG image, right? No. No, it's got JPG. That must be what it is. I can double click on it and it will open, right? Right? So I double click on it. It says, "Oh, Windows Photo Viewer can't open this image because it must be damaged, or it's too large." It's not a JPG. I put mine in the Dropboxes, but let's just sort of ask some basic questions. I haven't shared it yet with you guys because I'm not sure what we can do. Because someone said, "Oh, can we really open these images? These are real MRI images of my knee." Not that my knee is gonna embarrass me or anything. It's just a knee. But I'm thinking, we should be able to open these things. And so my first question to you is, how do you tell what kind of image it is?
Can you right-click it?
Sure. Yeah. You can right-click it. You bet. It's a file.
Click properties.
Oh, sure. Yep. You can get the properties.
Tell you in there.
Nope. Absolutely not. No. It would if only it were that easy.
Are we sure?
Are you sure? What do you mean, am I sure? I'm the professor. I should know. If I don't know, who are you going to ask? Huh? I'll paste it into my images directory. Then I'm going to mouse right on it, and I'm going to hit properties. Okay? Does that help you? It's 285 kbytes. It's a file. Okay? It's a file. Any other questions? So, details. You want details? Sure, I got your details. Here's your details. It's in the images directory, and it has a name, and it's a file. Got that?
Yeah.
Okay. What does that tell you? Bupkis, right?
Yeah.
Yep. So, back to my first question. How do we tell what kind of image it is? Don't know. Shrug your shoulders, give up, that's it. And Professor Lyon has to go through the rest of his life in pain because we can't see his MRI images. Too bad for him.
Well, we could open the software they have at the doctor's office.
They have software. I took notes. I know what kind of software they have. I can't afford that. So I'm going to have to write my own program in Java to view my own knee. How about that? But my first question, which was, yet to be answered, how do I know what kind of image I have?
How many different types of images can there be?
That's a great question. The number of different types of images. How many different types of images can there possibly be? I can make up my own image type, right? You can make up we'll call it the Mike image. We have the Kyle image. We have Kevin image file format. And of course, there's the Doug Lyon image file format, which everyone should use. Everybody can make up their own image file format and deploy it on the web. So the number of different possible image file formats there are is equal to unbound and ever growing. Not only that, because not every single browser is going to be able to decode every single image format, we're going to have to not only supply image data, we're also going to have to supply a mechanism whereby image data can be decoded. How could we possibly do that? To get a decoder on demand, you need to run a program on demand. A program written by a person who knows about this image file format. which means the program has to be written in Java, of course, because Java is the only place you can go to write a program that gets executed on demand. It has to be a Java applet or a Java Web Start application, because those are the only, unless you're going to write it in Flash, there's the only, and a lot of times you can't even run Flash, they're the only programs that are going to run on demand, right? C# won't run on demand. C# will not let you deploy an applet. Pascal, Fortran, COBOL, Snowball, I don't care. Well, you name it. It ain't going to run a program on demand, right? The only one that does that is Java. And so what you can do if you want to write your own image file format is you can write an encoder and a decoder, and you can write them both in Java, and you can decode on demand and encode on demand. So there it is. We've got this image file format. We have to write a decoder for it. How do I know what kind of image it is? Have to write a program. Yeah, okay, good, good. And what will this program do? It knows about different types of images. Good, good, good. I love it. So what did I do in order to try and write this program? I created something called the Stream Sniffer. The Stream Sniffer. And the Stream Sniffer does something that you will rarely see in most image processing programs. And in fact, you can find the Stream Sniffer with relative ease, just like all my code, just by doing a find in path and just write Stream Sniffer. And the Stream Sniffer is documented, by the way. It's documented in chapter, I think it's chapter 6. It's on I/O and readers. Is this my book? Yeah. Not your book. Okay. So if you wanted to, you could read all about it, the Stream Sniffer, and it's, I'll tell you exactly where it is. I thought it was chapter 6, but I could be wrong about that. Let's just make sure. It's, yeah, file input stream. The Stream Sniffer class is described on page 137. And the goal of the Stream Sniffer is to look at a stream. To look at the first few bytes of a stream, map those bytes into a list of known images, and then push the bytes back. And there is an interesting thing that you can do about streams, right? When you take a stream, you have an unformatted sequence of bytes. And what you want to do is you want to sniff at the stream by looking at a few bytes, and then instead of having the marker on the stream advance, you reset the stream. You push the bytes back so that you can take the information you've learned about the stream and pass it on to the next program. So it's very interesting. It's called a pushback input stream. Very exotic, rarely used in I/O, but it's one of the things that I thought would be a really good application, because I really do want to know what these streams are. Now, you could say to me, but Professor Lyon, don't people always name their files appropriately? And if it's a JPEG file, it ends with JPG, and if it's a PNG file, it ends with PNG, and if it's a GIF file, it ends with GIF, and if it's a TIFF file, it ends in TIF or TIFF, and you say, yeah, that would make sense. Wouldn't that be swell? But hey, look at what happened. I went to the Advanced Radiology Imaging guys, and what did they do? They gave me a CD full of files with absolutely no guidance on how to decode it, because the people who make these CD-ROMs are not Java programmers. They're not programmers at all. They're secretaries in a busy office trying to deal with Obamacare. And they're so overwhelmed with paperwork, they don't have a clue what to do. So you go to these people who don't want any extra work, and you say, oh, what kind of image is that? And you guess what you're going to get? Thrown out. So you're on your own, buddy. If you want to decode the images that the office gives you, you have to figure it out by yourself. So the Stream Sniffer, which is oh, it's a little slow. 43 occurrences. Oh, it's in there a lot. Get image Stream Sniffer. That sounds about right. Let's find out where that's at. You don't have it? Really? Let me just make sure I can give you a proper location. It's under Feudals in Stream Sniffer. And it's a file utility. And what I'm going to do is I'm going to look at the header. And I'm going to define the header as being the first 6 bytes in a file. And then what I'm going to do is I'm going to try and create a database of all the different file types that have to do with images that I know about. And I'm going to assign those file types some sort of an identifier. And so what I'll do is I'll say, let's see if I can find this. Yep, here we go. What I've got here is a list of, I'll call them public static final constants, right? And these constants are just numbers, but the numbers are associated with variables that have semantic meaning to me. And so if the file is not found, it'll come back as a 0. If it's UU encoded, that's UU, Unix to Unix encoding of a file, it comes back as a 1. If it's a portable gray map image, it comes back as a 4. If it's a portable bitmap image, it comes back as a 3. I made up the numbers just to try and categorize these things nicely. And so what I did was I went to all the databases I could find, looking for all the images I could find, and I just kept researching it and looking at it, and I realized, you know, here's the first 49 images that I know about. And image file types. Right, I should say file types that are used for images that are common.
Yeah, these are the 40 most common.
Most common that I know about. And some of them are not even image types. Like, for example, jars, you know, look like they're just Java archives, but you can use them to store images. PowerPC is an actual executable used for older Macs. HTML is a classic file type that you might encounter. It's not really for images, but I put a classification for it. So then the question became, you know, how am I going to determine what type of image it is? And so what I did was I create what's called a file input stream. I pass it into my stream sniffer. Then I take my stream sniffer and I call classify the stream, and it returns my image type. Then I close the file input stream and just return the image type, and then I'm done. So that's my main sort of get file image type. So I pass a file in, start up a stream sniffer, it goes, what's that? And then it says, okay, here's the type. I either don't know it or I do know it, and here's what it is. And so then the question then becomes, you know, what's this stream sniffer, and how does it handle a file input stream, and how does it classify the stream? That's so important. So here comes the arbitrary input stream sniffers can sniff at. Now, your arbitrary input stream, let's think about this just a moment. An input stream is an interface in the java.io package. An output stream is also an interface in the java.io package. Implementers of these interfaces include things like a file input stream, a file output stream. A URL can be used to create access to something on the web, and I can get an input stream off of that, and even supply an output stream. So anything that can give me an input stream and an output stream implementation will allow me to take an unformatted sequence of bytes and read or write that data. And so what does that mean to me? The programmer is that all I need to do is provide some source of data, bytes, and I can read them and sniff at them, and then I can do something non-destructive with them in order to figure out what's going on. And that's all I would like to do. Now, if you think about it, this idea has a certain amount of overhead to it, and it also requires a certain amount of, I'll call it, bit flipping and bit manipulation and string comparisons, and you know, the kinds of things that are tedious and boring, but I think are worth looking at. And so what I did was I decided there would be a couple of ways you could do a match. You could match based on characters that you find, or several characters, and then you can compare bytes with characters. And here you can see bit manipulations that are being done where we mask a character, look at the least significant 8 bits, which is the least significant byte in a 16-bit quantity, which is an unsigned char, and then compare it with the 4 bytes that come in. So if I give you 4 different characters that you might see, this will take those characters, take the least significant bytes out of the characters so we can see what they would look like if they were ASCII bytes, and then do bitwise comparison. So if GIF images start with exclamation point GIF, then I should be able to say, look, you can match exclamation point GIF as 4 bytes. The first byte is an exclamation point, the next byte is a G, the next byte's an I, the next byte's an F. In other words, it's not doing a standard string match, it's doing a binary string match by taking apart the characters, looking at their least significant bytes, and then comparing those bytes against the bytes that it sees in the file. Because the bytes that you see packed into a binary file are just looking like a sequence of bytes and not looking like strings, and you're not going to promote them into strings. And so that's one of the reasons why you get involved with these exotic bit flipping junk, right? So if you see it starts with a begin, that must be a UU encoded thing. Okay, now you look at this code, and the first thing that is going to strike you is, but Professor Lyon, if it starts with this and then return that, and if it starts with the other thing, then return the other thing, and if it starts this, then return that, it sounds like this is not a very object-oriented way to do anything. But you have to do it this way. I can't think of a better way to do it. You could say, but Professor Lyon, why aren't you using a switch statement or a case statement? That would be a good idea if case statements had a certain capability which they don't have. What capability would that be? The ability to dispatch on a string. Case statements require that you have scalar inputs, right? Case statements can dispatch on integers and shorts and bytes and chars, but they cannot dispatch on longs or floats or doubles or reference data types like strings. Why? Why can't they do that? Well, because switches, case statements, essentially take the number that you have in there. Let's say it's a char or x is an int, and then it says I'm going to do what's called a non-local computed goto. I'm going to get an address from that number, map it to a table that will essentially tell me what to jump to. And so what happens when you have a switch statement is any compiler worth its salt is going to do a non-local transfer of control based on an address, and it will compute that address and it will jump straight to that address, so that the switch statement is a terribly efficient way to do a dispatch, but not a particularly flexible way to do a dispatch. So if what you want to do is dispatch on a string, if the user types open, you do the open thing. If the user types close, do the close thing. Case statements can't help you. So that's a problem. So I end up having to write this rather large dispatch. Now later, if somebody enhances Java to include a case statement that works with strings, and I think they may have done that with JDK 8 or something, then I can revise this code. But of course it won't be reverse compatible if I take advantage of the new language feature. So now you've got a bunch of different ways in which you can look at, I'll call it the magic starting string. If it starts with P6, it must be ppm raw bits, whatever that is. But I can also do comparisons based on integer numbers. I can do comparisons based on characters. It turns out GIF images come in 2 different flavors. One's called GIF 87A and the other is called GIF 89A. And one of them has the capability of doing animation. So GIF images, I don't know if you're familiar with GIF images, but if you have 2 images that are in the same GIF animation, they have to use the same color lookup table because GIF images only have 256 colors. They're only 8-bit images. So when you have a GIF animation, all of the images in the GIF animation share the same color lookup table. Moreover, GIF images always use a lossless codec known as Lempel-Zev, which is really like zip. And so what that does is it gives you a dictionary of lookup codes. So if it sees a commonly held bit string, then it takes that and maps it to a short code and then gives you a code book. And the code book is essentially an efficient way to code commonly occurring bit patterns. So that's what Lempel-Zev does, and that's what they do for GIF. So as a result, GIF is very good for certain kinds of images which lend themselves to the lossless Lempel-Zev encoding and only need 256 colors. That can mean grayscale images or images that have been color limited. There are things like if you find it starts with an SND, it must be an audio file. If it starts with RMF, it must be a Microsoft RIF file, which is another audio file. So I can detect a whole pile of different file formats, and then to do quick lookups between integers and the strings that these integers map to, I have a hash table. And so the hash table allows me to do a lookup based on strings to get an integer. Normally, if you want to map an integer to a string, well, you can use an array of string. And that's easy, because then your integer goes in to the index, and then the string comes out. But if what you want to do is map a string into an integer, well, then the efficient way to do that is with a hash table. Do people here know about hash tables? No. Never used one? Hash tables are buckets. That's buckets that are like, for example, I'll give you an example that's sort of what can I do? I was going to use physical. Here's a physical. Suppose I had one bucket. Okay? Here's one bucket, and I put all of my stuff in this bucket, and then you had to sort it. The time it takes to sort might be something like n log n or n squared, depending on your sorting algorithm. But suppose I used divide and conquer, and I took n and I cut it in half and put half of it in one bucket and the other half in the other bucket. Well, if I can do that, then when I search, I can, if it's already pre-sorted, I can effectively cut the amount of work in half. With a hash table, what you can do is you can use what's known as a hashing function, which essentially takes something like a string and gives you a number. And that number ends up allowing you to decide which of the buckets to put the string in. So then when you want to go looking for the string, you can either look in this bucket or you can look in that bucket. But with a hash table, typically you don't have 2 buckets, you have like 100 buckets. And so what that does is it says, okay, I can take n, divide it through by 100. Using my little hash table, I can go into these buckets and figure out, where the string is at. So it makes string search constant time. And so all you need to do is have enough buckets and a good hashing function.
So now I think I use this in Oracle, not in Java.
Yeah, well, hashing functions are available to you in every language. Every language. So that's one of the ways in which I can map efficiently a string into a number. And so now what I'd like to do is run my little stream sniffer. It should prompt me for an input file. And what I'm going to do here is I'm going to find an input file with a relatively well-known file type. Here's one called jar. Now let's open it up and see what it says. And he tells me in hex what he found. He tells me in base 8 what he found. And he says, fee, fi, fo, fum, I smell a type not found file. So he couldn't figure it out. Right? It's not working for him. So let's try and go again. Only this, and I think it should have found the jar file, because here, if it starts with jar, it should be a jar file. So let's find it. Yeah, let's give it something that maybe we know it should be able to figure out, right? So here's data, images, GIFs. Let's give it a GIF image. He says, fee, fi, fo, fum, I smell a GIF 89. So that's pretty good. Let's.
The folder was too big, probably, because it looked like it didn't find anything in the pixel.
It did look like it was having trouble. Let's try this small map GIF. And he says, yep, that's a GIF 89. So he can tell by looking. Let's look at some of these color images. Here's a JPEG, open, and he says, aha, I smell a JPEG. Now let's go again. Oh, isn't this fun? Now somebody said something about, oh, what kind of image is this? Well, I don't know if he knows it. Let's see. Open it up and it says, I smell a type not found. So there's something about this file we just don't understand. Go again, no. So there's, how can I deal with a file like this? Anything else I can do?
Well, we know it's not one of these.
It's not one of these, right? I'm going to guess that my image processing program can't read it because it doesn't know this file format. There are other image processing programs maybe more appropriate for me to be using. Yes, there is a program available. Let's give it the name ImageJ. So ImageJ is a program I could run, and it says here I can download it for Windows, and it's bundled with 64-bit Java or without Java, which is probably okay because I already have Java installed. And it comes down as no JRE setup, and let's open that when done. And that's from the National Institutes of Health. So they've got a little program that they've been developing for a while, and then they stopped developing it. And the fellow who was doing that, who I think is now retired, is Wayne Rasband. And I did say open when done, right? Did it forget to open it? Oh, there it is. Run. Next, 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 next. Launch. The program will now be auto-configured. Configuration was successful. That's nice. Okay. Is it going to run now? I would hope so. Firewall allow access. Okay. Let's close that. Here's my little image file. Let's do an open. And now what we want to do is find that image file I couldn't read, which I'm thinking is in the data directory under Lion. And here it is. No? I thought it was in here. There it is. Open. And look, he can read it. Look, it's a knee. It's not a particularly high-resolution image, is it? As a matter of fact, it's 320 by 320 in 16-bit.
Possible when they give you the copy, they give it to you as like a low resolution, so you don't go to another doctor and get your own opinions or something like that.
Well, in fact, that's exactly why I wanted it.
Yeah.
I want to do my own opinion. So how do we know what kind of image that is? Let's do another open. What kind of file could this be? All files. Doesn't tell us. How do we know? Does this tell us anything? What kind of file it is? It knows how to read it.
No, like the MRIs I've seen like that too. They just
They know how to read it, yeah, but when they look at it, it's probably in a higher resolution.
Yeah,
But when they made him a copy of it, they probably did like a low resolution copy. Because that's what, photographers do the same thing. If they give you a CD to pick pictures, they don't give you the best quality because you would just go and print your own images at CVS or whatever.
yeah, that makes sense.
So he says it's a 16-bit image, but he doesn't tell me anything about what kind of image it is. Yet he was able
Is
to...
there a way to look up what this J-image program, what type of images they can read?
Yeah, you could probably Google it. You want to do that?
Well, otherwise we're stuck.
Well, why don't you do that? That's a good idea.
This computer doesn't have internet. It seems like
Your computer doesn't have internet.
Well, this is my temporary note-taking computer.
Well, does anybody have a computer with internet?
Yeah, this one's.
I mean, here it says I can save it as a JPEG, but I would rather just be able to read it directly. Save it as a JPEG. Yeah, sure, why not? But that just, that just gets me around the problem that I couldn't open it directly. I really wanted to open it directly. Utilities. It doesn't. Oh, image properties. That sounds promising. Let's see. What does he have to say for himself? I'm not seeing like an image type. All Java properties. Java virtual machine spec. And that's it. He doesn't tell me.
Did you do file open?
I did.
Well, it says file open command opens up TIFF, GIF, JPEG, PNG, DICOM, EMP.
That's what it is. It's a DICOM image. That's exactly what it is. I happen to know. So there must be a problem for me because I don't know what DICOM images start with. So that's one of those basic things. I mean, there's got to be a nice way to open up DICOM images in Java. So how do you open DICOM images in Java? There you go. Open DICOM viewer. A Java DICOM viewer. Let's see if that works. DICOM image viewer.
There are special DICOM options in ImageJ. I'm about to change the name.
There are DICOM options?
Yeah. Go to edit options. There's like special. There's like a few
Edit options? What do I do?
It says most.
I don't know if that's like relevant, but
Yeah, I don't see how that's relevant.
Yeah, it would make sense with DICOM. It says here that that's the most popular medical imaging is DICOM.
Yeah, I think that must be right. And there's the DICOM image viewer. So it says here, simple DICOM reader. And it's 7-zip extract to SJDR, I guess. SJDR. Here it is. And what does that buy me? Run with JRE. Open. Does that do anything? Read me. I have to read the directions. Here's a DICOM viewer. That's nice. So how do I use this? He's not giving me a hint. Extract to app classes. Oh wow, he's just giving me the byte codes. I need the source code. I'm not gonna try and decode the byte codes. I'm not seeing it. Oh, there it is. CD SJDR 113 dir app classes dir Java main class. Look, it's the DICOM viewer. How cool is that? File, open DICOM file. Now let's go to the let's see, computer, lion. Are we having fun yet? Data, images, DICOM image, open. Error. Maybe it isn't a DICOM image. That's a problem. That's a problem. If it's not a DICOM image, we must be opening it with something else.
Well, there's a couple. There's what's that? Flexible image transfer system.
You found another way to open it?
No, there's other, it reads different types of things. You tested already for PNG and TIFF images?
Yeah.
What about BMP?
Well, this thing is not letting me run. Ignore. Well, I mean, I have the ability to test for all of those in my stream sniffer.
Yeah, that's what I mean. But DICOM wasn't in the stream sniffer, was it?
No.
Yeah. What about FITS?
Well, FITS is a floating point image library that's used for astronomy. I'd be surprised if that's what they used. Yeah. I would rather doubt that that's what they're using, but I don't wish to cast aspersions if you want to try it. You know, so I mean, right now we're still back to the, we've been able to read it, but we don't know exactly what format it's in. Although it does say it's a 16-bit image. And I suppose I can export it, save as, and now I could save it as JPEG. And if I save it as JPEG, I suppose my own program should be able to read it then. But think of how, crummy that is. JPEG is a lossy format. So now I've compressed the image. That's not good. So j2d.gui.main. I'll run my little program here. Then I'll do a file open, and we'll open the JPEG version, and sure enough, it opens fine. So after opening the image in ImageJ and then saving it, I was able to display it using my own Java program. Very interesting problem, right? Now, what can we do in terms of homogeneous point processing to my knee? How can we improve our ability to see what's going on here? You guys have read the book now, Chapter 4, Homogeneous Point Processing. Right? That was assigned reading, wasn't it? Didn't we assign reading? Chapter 4? No? We had a lecture. I kind of remember giving you an assignment. Did we miss?
I read it, but I don't remember off the top of my head.
Don't remember anything. So I'm thinking we actually did the lecture here on contrast enhancement. So I thought maybe what I would do is get my little histogram panel out, and I would do a uniform non-adaptive histogram equalization. Oh no, that doesn't look good. That's bad. Right? Because why? Because of this noise. Right? What about this here? Oh, look, the exponential histogram equalization is not good either. Right? Because why? Because of all this noise that it's amplifying in the background. So what else can we try and do? I wonder if it can open the original image. Nope. Gave me an error. Doesn't know how to open that one. I had a feeling you wouldn't. Any ideas? I can negate the image. Does that help it? Not so good. Here's the histogram. Check out this histogram. All of the data is clustered toward the high end. There's almost nothing going on in the low end. If I do a uniform non-adaptive histogram equalization and apply it, and then I show the histogram, I've spread things out a bit. But now we can see where the noise is at. It's this junk over here on the left. How about that? So based on that histogram, after histogram equalization, do you think maybe we could find a way to remove some of the noise? I'm not hearing a yes, but I'm also not hearing a no.
Could you focus on the lower bits?
Yeah, I mean, can we characterize the noise in this image? First of all, what is this noise? And how do we know that it's noise? You know, that's an interesting question. Let's start by asking a different question, maybe a simpler question. What's noise? Is it feedback? I think feedback is a different thing, isn't it? If I think about it, noise is. Let's think about this in a different way. What's a signal?
It's like the output that you get when you're imaging. It's like the actual object. So if you have taking like a cell image, the signal would be the closest representation of what the cell actually is, and any noise would be a false representation of that cell that appears in the image that you have.
Well, that's interesting because you gave it an image processing interpretation. But suppose I told you I had a microphone, okay, and it's one-dimensional signal input, right? So the microphone serves as as a machine that converts energy from one form to another, right? Sound is nothing more than a pressure wave in the medium of air, which imposes a mechanical force onto a transducer, which is able to convert that sound pressure wave into an electrical signal. Right? So the electrical signal is really nothing more than, I'll call it, a way to measure, using a different form of energy, sound pressure. So what we see, I think, from this sort of simple example, is that a signal is nothing more than a measurement. And that measurement is going to be imperfect, right? Because it is made in the context of some unwanted thing that we don't particularly care for but cannot avoid, and that is what we'll call the noise. So the measurement part, that's the actual energy that we're getting from the sound converted into an electrical signal, versus the, let's say, background random occurrences of energy. So in a resistor, for example, there's going to be some inherent noise based on bandwidth and the temperature of the resistor. And the reason why that noise occurs is because the resistor is a material property embodied item that has random molecular motion. And random molecular motions cause random energies to be created. So if we want to lower the rate at which, let's say, atoms are banging about in some material, we can lower its temperature. And when we look at Boltzmann's constant with the product of the bandwidth and the temperature, we actually can see the energy that we're going to output. And so what we can do, if we want to really lower the noise floor on any sensor, is we can lower its temperature. And in fact, that's why they have cryogenic cameras. And in fact, if you had a stereo and you immersed it in liquid nitrogen, you could improve its performance, supposedly, if it didn't, malfunction from being immersed in liquid nitrogen, by many dB. And you can compute the signal-to-noise ratio dB improvement based on the difference in temperature between ambient room temperature and liquid nitrogen. Your noise floor is typically given at something like 120 dB. signal-to-noise ratio. And when we think about signal and the noise, if you are doing a digitization, you're doing two things, right? Remember two things for digitization? What are they? What are the two things you do? You sample and you quantize, right? You sample and you quantize. And when you quantize, you basically take a continuous signal and convert it into a signal that has a finite number of steps. That's quantization. And if you have an A to D converter, usually the number of steps that you get is expressed in an integral power of 2 in bits. So if I told you I had an 8-bit A to D converter, what you would say is, aha, 2 to the 8 is 256, therefore there can only be 256 different possible values coming out of the A to D converter, even though you may have an infinite number of different values going in to the A to D converter. And then if you said to me, well, the voltage maximum could be 1 volt, the noise must be the voltage of quantization. And the voltage of quantization must be 1 over 256. That quantization voltage level is going to be your noise floor for the A to D converter, because that's much higher than the thermal noise floor that you would get by doing a computation using Boltzmann's constant. In case you've never seen it before, it's worth looking at. I don't know if you guys have remembered your basic physics. Did they not discuss Boltzmann in physics? They should do that, right? Noise floor, N-O-I-S-E, floor, using Boltzmann, B-O-L, Boltzmann's constant. I can never remember Boltzmann's constant, except that it's got a lot of zeros on it or something or other. So there's the power level of your noise, right? And so it's a product of Boltzmann's constant with temperature and bandwidth in hertz. And the temperature, is in degrees Kelvin. That's one of those things where if temperature really was 0, you would have like 0 noise power, which would be cool. Very cool. So you could use liquid helium and go near 0, and then you'd have very low noise power, very high signal-to-noise ratio. So using this formula, it's possible to determine the minimum equivalent noise for a receiver at room temperature. Room temperature, 20 degrees C, I think. Isn't that right? Something like that. And then you have to add whatever it is for Boltzmann's, for Kelvin, which is like 273. So wouldn't it be 283? But he's calling it 290. I'm not sure what room temperature is anymore. I thought it was 20 degrees C. So then anyways, he gives you a number in here in dB per hertz, a bandwidth. And so you still need to know how many hertz you have total in your bandwidth. So that gives me a sense of noise floor for radio communications, for analog communications, and it also gives me a room temperature limitation for something like an A to D converter. Right? So for example, if you told me I have an 8-bit A to D converter, I'd say, well, you get only so many dB per bit, and usually it's around 6. So that gives me like 48 dB per bit. That's not a particularly good signal-to-noise ratio. But if you said, I have a CD-ROM, or audio CD, that gives me 16 bits. Now 16 bits, that's like 96 dB. So now you're getting into what may be the noise floor if you go to perhaps 120 dB or so for a wide bandwidth sampling. Let's say your bandwidth is something like 44.4 kilohertz, because that's your sampling rate. Then all of a sudden you can get a power ratio in there that says, aha, I really need to do something if I want to go, let's say, out to, pick a number, 96 bits or something. Right? It wouldn't make sense to have 96 bits. It wouldn't make sense to have 100 bits. Right? 100 bits would give me something like 600 dB of signal-to-noise ratio. That makes no sense. You can't use 100 bits, not at room temperature, not with the bandwidth of audio. That's just a waste of bits. The only way 100 bits makes sense is if you take the whole sensor and immerse it in liquid nitrogen. then even then, maybe it wouldn't help you. So you know 100 bits, that's way beyond the noise floor. So there's a certain limitation that we have to deal with on these things. So now I'm looking at this thing and I'm saying, aha, I think I understand what noise is. It's the unwanted signal that has nothing to do with the measurement. And every measurement has this. All measurements have noise. And so I can say that there's a way to model the noise, right? And a model of the noise might be like a random number that appears in the background. I could make a noisy image. Right? You could do that yourself. You could generate a series of random numbers in red, green, and blue and create a nice noisy looking image. And that would be a good model of noise. But it's not the kind of noise we're seeing here, is it? Right? That image that we see here doesn't quite look like noise. Now, I have this thing in here called the border frame, and it says, right, I can put in a border. And I've got this other thing called a bottom border, and I can put that in. And I've got a left border, and I've got a thing here called the right border. So ostensibly, I can take images and I can cut out little chunks of them, and maybe isolate the part of the image that's of interest. Sure, there's edge detections. Let's apply this and
Isn't the noise sort of like the echo of the signal coming back, and it takes longer to come back through your knee, essentially?
oh, you're talking about, you know, in terms of
Why
the
the
sensor
noise
that's
is
here.
different.
Yeah, the reason why what you're saying may in fact be true for this particular kind of sensor is because they're doing what's known as the radon transform in order to get a 3D image. But you can see the edges that are being used here, they're not doing anything to reduce noise. In fact, what they're really doing is they're emphasizing the noise.
Do you have like some sort of tool that like traces, you know, like trace and like cut along the edge? Do you have that?
Yes, I do. What you're thinking of is an intelligent scissors, and I discussed that in Martelli's algorithm, which is under heuristic edge detection. Yeah, I could do that, but what you're really dealing with here with noise is you're dealing with some property of the signal, the noise signal, which is discontinuous. And when you do edge detection, what you're really doing is you're saying yes with a filter to sudden changes in energy. So what you're really doing is you're looking for a step change in energy, either energy going way up suddenly or going way down suddenly, or maybe having an inflection where it goes up and then changes direction. So those are the kinds of edges an edge detector is designed to emphasize. So it's taking a local derivative and looking for piecewise discontinuities. So edge detectors actually increase the amount the amount of energy you're going to get from noise. So in order to do edge detection properly, the first thing you do is you do a low-pass filter. And the low-pass filter effectively creates a form of what's known as continuity in the function. And there are several different kinds of continuity. There's C0 continuity. That's when functions are continuous, but not necessarily in the first derivative. There's C1 continuity. That's when the first derivative is continuous. There's C2 continuity. That's when the second derivative is continuous. And Cn continuity, that's when the nth derivative is continuous. So you would have that, for example, in a sine function, because you can take the derivative any number of times in a sine function, and that derivative will be continuous. But you couldn't have it in a, let's say, a trapezoidal function with a peak at the top, because it would have a C0 continuity. The function would touch at all points, but in fact, if you took the first derivative at the apex, it might go to something that's not defined. So it doesn't have the C1 continuity. You're out of here, huh? Okay. So the way you do this, if you want to, if you want to do an edge detection, is the first thing you do is a low-pass filter. But what I was thinking would be good is if we could characterize the noise in the image. So how do we characterize noise in an image?
I don't know if that's. I mean,
How about if we look at the standard deviation of the of an area inside of the image, and if we have things that are inside of that standard deviation quantity, then we would say that's noise, and if we have things that are outside of that standard deviation area, we'd say that's signal. So maybe signal changes locally more slowly than, let's say, the noise, especially when the noise is in a large area that can be segmented. So what I'm thinking is we can use a statistical mechanism whereby we measure areas inside of the image after they've been isolated. So that's an interesting idea, but it's probably not one that you guys are ready to implement yet. Right? What would it take for us to get you guys ready to implement an idea like that? And I think the answer to that is a lecture. And I happen to have one prepared, but I think first what we need to do is take a break. So why don't I stop this?